I want to introduce chapter 14. It is about waves in general and sound as an example of waves. First, we are going to introduce what are the two different types of waves, and then we are going to study the waves on a string. We are going to find how we can represent the harmonic wave functions, and we will move deep more in sound waves, talk about speed of sound, sound intensity, and the Doppler effect. We will be also able to study superposition and interference, standing waves, and beats. Now for the waves, we will say that maybe like we did study the previous chapter oscillations, and this is waves because there is a connection. Like the wave, it is a disturbance, it's an oscillation, and that is gonna propagate from one place to another. Then this is what's really happening with like a disturbance that is gonna propagate through space. There are two major types of waves. The first one, it is called transverse, and you will find that the oscillations are really perpendicular. Then this slinky here, it is moving up and down, and this is the direction of the wave motion. This is why we call this transverse. Then when it is perpendicular, you're going to find that there is 90 degrees between both of them. Also here, I want to use it to say that we usually say this is a crest and this is a trough. A crest or we call it a peak. The other type, it is longitudinal. The vibrations or oscillations are either parallel or anti-parallel to the direction of the wave. And you can see here that they are really going in this direction or this direction, and the direction of the wave is this one. Then, and this is, we call them longitudinal, and they are made up with, from like for the slinky here, you will find that there are areas where we're gonna have the rings are really very close. We call this compression. This one, when they are really far, we call it either expansion or rarefaction. Okay? And I will say here, we will, of course, define some of the stuff in here, but let me show you my YouTube about waves here. Okay, where okay, come on, library, physics.
Waves transfer energy from one place to another. You should already know how to describe them in terms of frequency, wavelength, and amplitude, which we looked at in another video. In this video, we're going to look at two ways they can be classified. Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. Whether they are transverse or longitudinal depends upon how the particles are made to vibrate as the energy passes. Let's look at longitudinal first. This is where the particles vibrate parallel to the direction in which the wave of energy is traveling. Notice that the ends of the slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions. An example of longitudinal waves is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on until the vibration reaches the ear, causing the eardrum to vibrate. The vibrating air speeds away from the source, creating a sound wave. Let's look at another type of wave, transverse waves. The hand moves up and down, as does the slinky, but the wave itself moves from left to right. So the particles vibrate at 90 degrees to the direction that the energy is moving. We can simply think of it as, in longitudinal waves, the hand pulses horizontally, pushing and pulling, and the wave energy also moves horizontally, back and forward. Whereas in transverse waves, the hand moves up and down, but the wave energy still moves horizontally. Again, the ends of the slinky never leave the hands holding it. It's just the energy that moves along. Transverse waves are usually used to show the wavelength and amplitude. Pause the video and see if you can remember how to label the amplitude and wavelength on the diagram.
All right, then this is really explaining to you the two different types. And as I said, like, okay, for the transverse, the vibration is perpendicular to the motion of the wave. Now, the wavelength, it is defined as the distance between any two successive crests or any two successive troughs. Okay, this is really lambda. Now, here consider a wave on a string moving to the right as shown in below. What is the direction of the velocity of a particle at a point labeled A? Here we're gonna find that this particle, like momentarily, is gonna be at 0. Then this is the velocity oscillating particle is gonna go into one point where it's gonna like having 0 velocity at the maximum displacement. Whereas here, if we are going to consider a wave on a string moving to the right as shown, what is the direction of the velocity of a particle at the point which is really called B? We're gonna find that is gonna be upward, because I want you to look at like later what's gonna happen to it is gonna go up, then like the value is gonna increase, because remember, like I will say the energy is the one that is really moving or transported. It's not the object. Here also talking about the compressions and rarefactions in the other type, which is the longitudinal, we can also have lambda between any successive compressions or rarefactions. Now, does a longitudinal wave, such as a sound wave, have an amplitude? Of course. Okay, that doesn't mean that it doesn't have an amplitude. It has an amplitude, and the amplitude here is the maximum displacement from, like I would say, equilibrium. Now, I will say also here, all of them, they have wavelength. All of them, they have frequency, amplitude, velocity, and period. And all of these, as we discussed, and maybe like here, I want to say something about these. Like we did introduce these last time, but okay, I will say wavelength. It is measured in meters, and it is the distance between any two successive. Okay, let me talk about the transverse. It's easier. Successive crests. Okay, now I will say frequency. It is measured in hertz, and it is the number of cycles per unit time. And amplitude in meters, it is the maximum displacement from equilibrium, and velocity meters per second. Of course, it is the distance per unit time covered by a wave. And V has to do with lambda and the frequency. Okay. The last one, it is the period, which is measured in seconds. It is the time needed for one complete oscillation. Okay, these are really important. Also here, I want to remind you, T equals 1 over F, or F equals 1 over T. At a football game, the wave might circulate through the stands and move around the stadium. In this wave motion, people stand up and down and sit down as the wave passes. What type of wave would be this characterized at? I will say transverse, since it is perpendicular to the direction of the motion of the wave. Now, of course, examples on transverse wave, we can have the slinky in transverse waves, we can have strings in transverse waves, we can have sound waves longitudinal. Water waves are really a combination of transverse and longitudinal waves. Sometimes it's not going to be, we will not be able to maybe to strictly classify. Wavelength, lambda, distance over which wave repeats, and I said we can, like from the diagram, find it using the distance between two successive peaks or crests. The period is time for one length to pass the given point, and these are the equations that I gave you already. Now, boat is moored in a fixed location and waves make it move up and down. If the spacing between wave crest is 20 meters and the speed of the waves is 5 meters per second, how long does it take the boat to go from the top of a crest to the bottom of a trough? Then here we are not looking at like the whole period. We are looking at just half of it, because going from here to here. I have lambda as 20 meters. I have V as 5 meters per second. I can find the frequency, which is V divided by lambda. Or like I can use the other formula and find T directly. T, it is 1 over F, and then it is 4 seconds. And what they are asking about is half of a T, which is going to be 2 seconds. Now here, another example here, the speed of surface waves in water decreases as the water becomes shallower. Suppose waves travel across the surface of a lake with a speed of 2 meters per second. This is the first half of the, the first part, which is considered not shallow, and a wavelength of 1.5 meters. When these waves move into a shallower part of the lake, their speed decreases to 1.6, though their frequency remains the same. Okay, find the wavelength of the waves in the shallower. Now, here I will say, they said that the frequency is the same. Then I will use the first information, which is the velocity, V, the speed 2, and lambda 1.5 to find what is really the frequency. And the frequency, it is V divided by lambda, which is 2 divided by 1.5, it is 1.33, and then I will use the same frequency to calculate the second lambda, which is going to be 1.2 meters. Now, I can create waves, transverse waves on a string, and the speed of the wave is really determined by two important factors. The first one, it is the tension in the string, and the second one, it is the mass of the string. Okay, and here you can see that this is the setting. We have like a string. It will be attached to a vibrator that is going to make it vibrate up and down. And there is a mass that is going to represent the tension, which is the weight of the mass that is hanged here. Now, the total mass of the string depends on how long it is. And it's easier for us to represent the mass by having mass per unit length. Then it is mass divided by length. Sometimes we call it linear density. Then I want you to be open to the both. Either you're going to say mass per unit length, or you're going to say it is the linear density, its unit, it is kilogram per meter. Then I'm looking at 1 meter, what's the mass of 1 meter? Now, the speed of a wave on a string, as we said, depends on the tension and depends on the mass, which is mass here per unit length. And of course, it is measured in meters per second. As we can see, the speed increases when the force increases and decreases when the mass increases. Let's assume here that a wave pulse can be sent down a rope by jerking sharply on the free end. If the tension of the rope is increased, how will that affect the speed of the wave? Of course, here we will say since the tension is on the numerator, then the speed should increase. A wave pulse is sent down a rope of a certain thickness and a certain tension. A second rope made of the same material is twice as thick but is held at the same tension. How will the wave speed in the second rope compare to that of the first? Since now the thickness is going to be double, I will assume that then the mass is going to be double. And then I will say the speed is going to decrease because the mass, it is in the denominator. Now, I can make waves in a string, and then it will, if I have here a fixed end, then the wave is going to reflect and the reflected wave will be inverted. Inverted mean if it was really hitting with a trough, then when it's going to reflect, it's going to be a crest. And here we can form what is really called standing waves. There are certain frequencies that I will have standing waves, and I will talk about that. If the end of the string is free to move transversely, the wave will be reflected without inversion. Then it might, go this way. Okay. And then without inversion. Let me show you here this video related to this, okay, and that is going to be this one. Okay, you can see then when it is fixed, it's gonna be reflected, I will say, negatively, or as we said, it's gonna be inverted. Now, a wave encountering a denser medium will be partly reflected and partly transmitted. If the wave speed is less in the denser medium, the wavelength will be shorter. Let's try to solve this one here. A brother and sister try to communicate with a string tied between the two tin cans. I think like everybody did work with this like old phone. If the string is 9.5 meters long, has a mass of 32, and is pulled taut with a tension of 8.6 Newton, how much time does it take for the wave to travel from one end of the string to the other? First, I need to find lambda. Okay, sorry, why lambda? Why did I call it lambda? I want to call it like a mu. Okay, and then from that, I will be able to calculate V. V, it is the square root of T divided by mu. The tension, it is 8.6, and this is a mu. Then the speed is 50 meters per second. Now I can use here T equals distance divided by speed, and from that you will be able to get that the time it is 0.19 seconds. I will stop here for the first part, and then I'm gonna continue.